In the previous lecture, we started having a look at how we can turn ideas from logic into mathematics. And we got the basics down, but there are still some more logical statements that we need to be able to mathematize. So that's what we're going to have a look at in this lecture. So consider the following statements. I'm going to quit if I don't get a raise. If I pass the final, then I'll graduate. And I'll be going to the movies provided that my car starts. Now, all of these things are definitely propositions, because remember, a proposition is something that is definitely true or false. But they are all conditional. What this means is they can all be restated to fit the form if something something, then something. For example, if we wanted to rewrite the first statement, we would say, if I don't get a raise, then I'm going to quit. So a conditional statement is always interpreted as a guarantee. If the condition is met, so for example, in the case of the first one, if I don't get a raise, that's the condition. So if the condition is true, then the conclusion must be true. So here the conclusion is, I'm going to quit. If we wanted to rewrite the last sentence, for example, I'll be going to the movies provided that my car starts, we would rewrite this as, if my car starts, then I'll be going to the movies. And the condition here is, my car starts. If that's true, then the conclusion, I'll be going to the movies, is by definition true. That's all that this says. Note, and we'll see this as we're about to do the truth table, it doesn't say anything about what happens if my car doesn't start. So let's look at that in a little more detail. So our conditional statement is if condition, which we'll call P, if condition, then conclusion, has a truth table that looks like this. And we denote it with an arrow like so. So let's start with the obvious thing. If both the condition and the conclusion are true, then we say that the conditional statement is true. So if it's true that my car starts, then I will go to the movies, and this whole thing is true. On the other hand, if the condition is true, so my car starts, but I don't go to the movies, then the conditional statement isn't true, because I said that if my car started, I would go to the movies, but then my car started and I didn't go to the movies, so then it must be that what I said was not true. Now let's look at the other two cases. Suppose that the condition is not met. So my car doesn't start. Well, it doesn't actually matter what I do, whether I don't go to the movies or I do go to the movies, because in either case, the statement I made is still true because the thing that would have been needed in order for me to go to the movies didn't happen. So whatever I do, what I said was true. Let's take another look at this with another example. So suppose I say to you, if you get 100% on the first class test, then I will give you a chocolate. What we want to think about is when the marks for the class test come out, under what circumstances will the statement be true, and what circumstances will the statement be false. So let's think about that for a moment. So if you get 100% and I give you a chocolate, then what I said was true. So my statement, so this was our condition, and that was true. And the conclusion was true. And so our statement was true. On the other hand, if you got 100% and I didn't give you a chocolate, then basically I lied. So our statement was false. So in that case, our condition was true, but our conclusion was false, and therefore our statement was false. So those correspond to these two lines of the truth table. On the other hand, if you didn't get 100%, so suppose you get 99%, and I give you a chocolate, well, that doesn't make my statement false, because I only said that I would definitely give you a chocolate if you got 99%, but I didn't say that I wouldn't give you a chocolate I said I would give you a chocolate if you got 100%, but I didn't say I wouldn't give you a chocolate if you didn't get 100%. So this is still true. So here our condition isn't met, and it happens that I happen to make the conclusion true, and there's my statement true. But on the other hand, if you got 99% and I didn't give you a chocolate, you also wouldn't say that I lied. Because all I said was that if you got 100%, I'd give you chocolate. I didn't say what would happen if you got 99%. And so my statement is still true. So these two cases correspond to these two lines of the truth table. So in fact, you'll notice that for a conditional statement, the only case in which it is false is when the condition is met, but the conclusion is not met. So if we have a look at a slightly more mathematical example, here's a statement. If an integer is a multiple of 6, then it is even. So let's see how this works for some different integers. For example, suppose we think about 12. Now, 12 is an integer that's a multiple of 6, and it is true that it is even. So that definitely makes our statement true. And if we think about it, what we've got is that our integer is a multiple of 6, so that makes our condition true, and it is even makes our conclusion true. And so we get that P implies Q is true. On the other hand, we could have a situation where we have, for example, let's take 4. Now we have that our condition is false. So our integer is not a multiple of 6, but it is the case that it's even. So we have that our Q, our conclusion is true. So 4 is even, and so we haven't really said anything false because our condition wasn't met. So our P implies Q was true. Another case that we could look at would be if we take, for example, 7. Now we would have that our condition is false because our integer is not a multiple of 6, and our conclusion is false because our integer is odd, it's not even. But I still, again, haven't said anything incorrect because my condition was never met. So our P implies Q is still true. The only thing that would be weird is if I could find an integer that was a multiple of 6 that wasn't even. And in that case, my statement would be false. But we can't find any integers that are multiples of 6 that are odd, and so the statement is never false. Okay, so take a moment to work through these examples because it can feel a little strange. This is logic, but not as you know it. So the next thing that we want to have a look at is the converse of a proposition. So the converse, and we need to be quite clear here, the converse of a proposition P implies Q, so this is an if P then Q, is the proposition if Q then P. And before you think about the truth statements, the truth tables of these, let's just find some converses. So what is the converse of if you get 100% on the first class test, then I will give you a chocolate? Well, if we're thinking about this, our proposition says if you get 100% on the first class test, so that's our condition, that's our P, then I will give you a chocolate. So that's the conclusion. So this is P implies Q. So Q implies P says if I give you a chocolate, so this is if Q, then you will get 100% on the first test. So you can already start to see that the converse of a proposition doesn't mean the same thing. Let's have another look over here. If we look at our multiple of 6, an even integer thing, here we have if an integer is a multiple of 6, so that's our condition, then it is even, that's our conclusion. So our converse is if an integer is even, so that was our Q, then it is a multiple of 6. And you can see straight away that while we know that if an integer is a multiple of 6, then it's definitely even, it is not the case that if an integer is even, then it's a multiple of 6. So the converse of a true proposition is not necessarily true. We have something that sounds a little similar, but is actually quite different, called the contrapositive. So if we have a P implies Q proposition, so if P then Q, the contrapositive says not Q implies not P. So let's have a look at this. So again, we're looking at our contrapositive of if you get 100% on the first class test, then I will give you a chocolate. So you get 100% on the first class test. That is our condition. I will give you a chocolate as our conclusion. So our contrapositive is if I don't give you a chocolate, because that is not Q, then you didn't get 100% on the first class test. So that's not P. And notice here, now this contrapositive is true. And in fact, it's saying exactly the same thing, just in a kind of roundabout way. If I don't give you a chocolate, then we know that you didn't get 100% on the test, because I would have given you a chocolate if you had. And again, we can do that with our integer example. So here we have our P and our Q, and our contrapositive says if an integer is not even, then it is not a multiple of 6. And again, you can see if our statement was true, then our contrapositive is also true. So the next thing that we want to have a look at actually combines several ideas that we've just spoken about. So if P and Q are propositions, as we've been seeing before, the biconditional statement P if and only if Q, which we denote using this double-headed arrow, is defined by the following truth table. You'll have heard us also sometimes say if and only if, and we often abbreviate that to IFF. And what we're really saying here is that both P implies Q and Q implies P are true. So remember, we defined if P implies Q, then Q implies P was our converse. So our biconditional proposition is saying that a statement and its converse are both true. So let's see if this makes sense. So if P and Q are propositions, our biconditional statement, well, if P is false and Q is false, then we certainly we know that we have P implies Q is true, remember, and we also, if we swap it around, know that we have Q implies P, so that must be true. On the other hand, if we have a look at P being true, so our condition being true, and our conclusion being false, we know that P implies Q is false, and so we must have that our biconditional proposition is false. If both of our propositions are true, then one implying the other, so if we go P implies Q, we know that that's true, and we know if Q implies P, then that's also true. Finally, if we have a look at P being false and Q being true, now we want to make sure if we go P implies Q, then usually that would be true if we were just doing P implies Q, but we also want to think about what happens when Q implies P, because we want the converse to be true, and in that case it would be false. So we have another false over here. So let's have a look at an example. A triangle is equilateral if and only if it has 3 equal angles. So remember, we want to have P implies Q and Q implies P. So triangle is equilateral. That's going to be our P. If and only if it has 3 equal angles, that's going to be our Q. And let's have a quick check of our truth table. And we want to find out. So if we start off with a triangle that is equilateral, so our P is true, and it has 3 equal angles, then we know that P implies Q and Q implies P, so this is true. If we have a triangle that's equilateral, but it turned out that it didn't have 3 equal angles, well, then this wouldn't be true. If we have something that is not equilateral, but it has 3 equal angles, then our if and only if is false. And finally, if our triangle is not an equilateral and it doesn't have 3 equal angles, well, then our statement has nothing to say. It's still true. So see if you can work through these ideas, checking this statement. A number is divisible by 9 if and only if the sum of its digits is divisible by 9. So see if you can think through the truth table for this.